So the next
Thank
speaker
you.
is Gerard Bricogne. So Gerard is a research director at the CNRS in France. He's also director of global phasing, and he's actually going to talk about the refinement tools in global phasing today. So Gerard actually has originated many novel mathematical ideas in crystallography, such as application of Bayesian statistics through maximum likelihood. Actually, he has already been introduced a few times in a few different talks before, so I don't think there is much need to introduce him further, so please, Gerard. Gerard, you're muted.
Yes, thank you for the introduction. Just one small thing, and it's all my fault for having sent my CV too late for it to be read. I haven't been at CNRS for a decade or so, just pure global phasing for quite a long time. So I will not be covering a sort of point-by-point comparison between Buster and other refinement programs. I would say that Buster offers an essentially similar range of capabilities to other programs in terms of parameterizations, restraints from general structural chemistry. That restraint topic was covered by Clemens very well yesterday. Grade and grade 2 to generate ligand restraints. Unlike the other programs that have a wealth of features now for looking at neutrons and cryo-EM, as well as X-ray diffraction, for the moment we are limited to X-ray diffraction. On the other hand, what I will describe is more the way in which refinement around Buster is coupled to various other processes, especially on the data side. A way of questioning, of interrogating the data at the refinement stage in a way that has been prepared by data processing is these early minus late map coefficients that we introduced some years ago. The early and late partial data sets are produced by autoproc if the redundancy is sufficient. And these maps, I think Clemens has presented them on a number of occasions, are very good at spotting radiation damage, and that can convey important information. Also, in terms of infilling output map coefficients by DFC values, we do that only for data that are missing within the anisotropic cutoff surface. When you have strongly anisotropic data that avoids biasing the maps towards pure FC contributions outside the cutoff surface. We have put some effort into validating the refinement results, especially geometry and density agreement for ligands. I will cover this, and mostly I will cover some tools that we use to investigate sources of disagreements between model and data in data space. So in reciprocal space for merged data and in diffraction image space for unmerged data. That will not include any earth-shattering results, just a quick demonstration of these tools. And if I can manage to get through this in 15 minutes, I'll feel lucky. I will also mention an effort to deposit richer content into MMSIF deposition files that can help towards these sort of data side troubleshooting problems. So validation capabilities. We have had Buster report for over a decade now. These are two diagrams, one of them for a defunct PDB entry before remediation and after re-refinement with Buster and correction of the restraints and a number of things. That was done 10 years ago by Oliver Smart. These diagrams are quite photogenic actually, and very quickly I will mention that Josane Marquez's high throughput screening pipeline at EMBL Grenoble annotates the results of running pipe dream through large numbers of data sets by these diagrams, sorted on ligand density correlation coefficient. But let's get back to Buster report. There are not just pictures of ligand pose in density, but also an illustration of how well the geometry of the ligand agrees with ideal geometry queried via Mogul from the CSD. And you can see that the remediation has done a lot of good. Everything is green. It's a pity that the diagrams are not exactly in the same orientations, but never mind. This has had some success. The PDB has adopted the same extra information, the generation of the same information in its validation report. And in fact, the code that generates the diagrams was donated by Global Phasing. So you will see these diagrams and the density around the ligand in every validation report. Now, validation, there is a lot of talk about validation when AI produces models that are certain to be in agreement with everything you can throw at them in terms of geometric validation. So let's have a look at what can happen if validation gives you problems. You may have to rebuild in the light of better map. But what if the maps and various bits of density remain confusing? Could that be because of shortcomings in the data? And we have very simplistic ideas often about shortcomings in the data. So to make those ideas more precise and the tools more useful, we have developed three main tools: the reciprocal space correlation plot, which gives several types of correlation coefficients, the log likelihood outlier detection plot, and a data auditing process. So reciprocal space correlation plots have been in Buster ever since the beginning, maybe 25 years ago. There is always a red curve and a blue curve. The red curve is the observed agreement between FO and FC. The red curve, and the blue curve is the agreement we would expect if the variance model for the prediction around FCalc, so the D factor, is correct. There are other curves. The yellow one gives you completeness, and the green one tells you the maximum correlation you can hope to achieve given the noise in your data. And between the beginning and the end of a refinement, you can have this rather pleasing phenomenon. It's probably a bit too close here, so there might be some overfitting. This is often accompanied in a montage by R-value progressions and the progression of working and free log likelihood gain per reflection. So this is a very standard tool. The interesting thing is that it tells you more than R values. R values, in a sense, are contained in correlations, but it can give you a lot more information, and especially the adequacy of the weighting by prediction variance. So let's look at a few examples. This is a rather tormented plot. You can see that there are notches in the completeness. We will see why in a moment. There are also what we call icicles in the red curve. There are also upward facing icicles here, which means that the sigmas have been underestimated. And a further feature is that here it seems that the unfiltered, unsatisfactorily filtered ice rings are not quite at the expected resolution. So regarding those notches and module gaps, this is a picture that you can get by looking at the deposited data in PDB PEEP. And you see that indeed there are tiger stripes, as we call them. In fact, concentric cylinders of missing data around the cusp, because this is in P1 and somehow the beam was not off-centered from a center of symmetry of the module gaps. Okay, another example here. We see another case of ice rings having been removed at the wrong resolution, leaving one of them which of course is seen here in the log likelihood outlier plot. The final example is just a plain example of ice rings not removed. So icicles are incompletely removed. They were removed a little bit since the completeness dips, but here the loss of correlation says there's still a lot of problematic data there. And indeed, they show up as low log likelihood measurements. The difference between this plot and the log likelihood outlier plot is this compares observations and predictions in resolution bins. Here, it's on an individual reflection by reflection, merged reflection by merged reflection. So there is somehow information attached to each of those dots, and maybe we can present it in a different way. And this is the purpose of data auditing. Where do these outliers come from? I will just demonstrate the tools that we have been developing, which are still in development, but have been trying to exercise in a useful way. Here is 6VZU. If you look at the validation report, you don't worry about anything. It has actually just the right vital statistics on all these criteria. However, the reciprocal space correlation plot just looks as if there's just something preventing it from aiming higher. There's a big gap here. And this is what enabled us to pick up this example, together with the fact that the log likelihood outlier plot shows an unusual abundance of outliers. We rarely see that. So as I mentioned here, we display all those dots binned by D star, but still distinct. So we can rearrange the labels of all these dots in such a way as to see what unmerged reflections each measurement came from. So this is where we need unmerged measurements to be available, sufficiently annotated by instrumental attributes such as image number, but also detector surface coordinates. And here we see that it's not just a sort of general unhappiness from a noisy background. There's a very systematic structure in where those outliers are found in image space. If we look at the detector surface, either highlighting by intensity or highlighting by the profile correlation produced by XDS on integration, we see that these are perfectly well integrated reflections. It's not a matter of truncation on module gap boundaries and that sort of thing. So what can it be? Well, if we then go to the images themselves rather than to the labels for the reflections that were integrated out of that, and look at what Autoproc said when it processed this, we see that there are two areas where there is a large number of unindexed spots. And these correspond exactly to the image ranges shown here. XDS also says, oh, there is really quite a concentration of misfits. That means conflicting measurements between symmetry-related reflections. So let's have a look at the images themselves. So this is an image in a good range. You see that the spots are well indexed. The loons are well defined. There is no messiness between the loons. On the other hand, if we look at an image in the first peak where there are outliers, we see that it's not so good. There are spots outside where the indexing has been done. There are spots between the loons of the lattice on which data were indexed. In the other bad area, the same sort of thing. So what to conclude here? Can we at least understand why these outliers are there? Well, the crystals are monoclinic. They have a beta angle very close to 90 degrees. And the structure has NCS. And Ian Tickle had a look at this and found that the asymmetric unit is actually a 2-2-2 tetramer with axes almost parallel to the cell axes. In that case, the twinning tests that are done here in STAR and ISO or PDB PEEP show that there is no twinning. The intensity statistics are perfectly untwinned, but some of the twinning tests that look at relatedness between potential twinning law axes are picking up NCS and interpreting it as twinning. So we can contemplate the explanation that there must be some small crystallite attached to the main crystal that contributes in some image ranges, maybe by being stuck to the crystal and entering the beam and exiting it the rest of the time. Of course, we have to confirm this by further work, but I was telling you, I didn't promise an earth-shattering result, only a kind of demo of the tools. Maybe the structure can be improved. It has two types of ligands. One is well fitted, the other one not so well. So
5 minutes remaining.
Okay, what's the rationale of all this? Which is that it is bad science to throw away data simply because they do not agree with the model. This is a mantra we see on the CCP4 bulletin board all the time. However, sometimes you want to get rid of perturbations introduced by strong disagreement, but to have a clear conscience, you want to make sure that you can explain their source. And if you just say, oh, well, they are so outrageous, they have to be errors, I'm neglecting them, you'll probably be doing okay. I think the other refinement program have various thresholds that we haven't introduced ourselves, but you can sometimes miss the opportunity of having useful diagnostics of malfunctions. So what is essential here is to be able to follow the wires backwards from merged to unmerged data. Another source of rogue data can be the handling of misfits. I don't have time to cover this. It's a lovely piece of work by Clemens, and who realized with horror that sometimes in XDS, if you have many agreeing good measurements, but you have, because of shadowing, one of the symmetry equivalent, which is 0, somehow a precision criterion will result in the 0 measurement being considered as good and the others rejected. You can imagine that this can play tricks in creating outliers. So to broaden the subject further, and it's been mentioned many times in remarks, it's important to be able to assess how reliable a deposited structure is, or structure being worked on. After all, AlphaFold has worked from the contents of the PDB and probably found that not everything was equally worth paying attention to. I've presented tools that already show what you can do to pick up troublesome measurements and see where they might come from. But that entails a lot of work, and it's difficult to share. So an idea we've been sort of working on is that it would really be useful if each deposition could be enriched with supplementary data and quality metrics that would make it easier to assess, in a sense, how well the structure is backed up by the experimental data once one has removed everything that one has understood to be a contaminant. And
2 minutes remaining.
Okay. Ideally, we would want to make the PDB searchable for structures that are supported by data of sufficient quality that would be characterized by thresholds on these archived metrics, and not just the archived metrics in the validation report, which are so sparse. Just resolution, R merge, and the I over sigma at D star max, which validates the resolution, but gives no indication of the quality of the data themselves. So this has started to happen. I can't say very much about this, but at the end of March, we have worked with a subgroup of people with the PDB XMM-CIF working group to archive extra items, 50 items related to data anisotropy, unmerged data, and anomalous data. The next step, of course, to broaden further, will be to not just better archive the data that have been collected, but archive data that have been better collected. So that's also been one of our preoccupations, and we have developed a workflow to enable consistent, high-quality data collection. And I can't stop myself from showing just a couple of very quick slides from Ashwin Chari, 2 data sets collected with the same total dose on a crystal with a gigantic asymmetric unit, but diffracting to very high resolution. The data statistics for what was collected with the workflow are better, but a nice comparison of maps here. You can see, again, same total dose, but you can see clearer features that are significant with the data collected with the workflow. And I would like to put up this acknowledgement slide. Everyone at Global Phasing has worked very hard on tying all these different methods, and the subgroup on data collection at the PDB that has unfortunately recently lost John Westbrook has been extremely stimulating in this sort of long-term goal of enriching the PDB. Thank you very much. And have I gone over? I've got 1 minute.
Yes, yes. Thank
There are
you.
probably
Thank you, Gerard.
so many possible matters to follow up that it's best kept for outside the question and answer session.
Thank you, Gerard. It's very nice and stimulating talk. We are over the time, but I think that they will allow 1 or 2 questions to answer. And one of them is that they can, Roger asks that, can you index and refine a second lattice in the data set?
We will have a look at it. Usually Autoproc is pretty good at picking up secondary lattices, but where we saw extra spots, they seem to fall practically on the same lattice. But we need to revisit this with perhaps more sensitivity to that detection. That's part of the follow-up.
Okay, thank you. And there's another interesting question, which I would like your one sentence response. That what do you think about the discarding data, for example, not only in crystallography, in single particle cryo-EM, a lot of particles are discarded. I think that is a more general question. I want your one sentence answer, then let SLAC to explode.
Okay, well, I would say it would be important to explain why they are rejected. So if there are good particles and then bad ones are not worth including, it would be good to characterize or find an explanation for why they are bad.
Thank you. It is very
Pretty
good.
obvious.
I think that let's just have the rest of discussions on Slack, and I think it's extremely important point that what is outlier, what is wrong, what is noisy, and it's very difficult to distinguish them. But I think that is it. There should be more general discussions. Okay, thank you. On now, our next speaker.
Thank you.
So the next speaker.